I'm MMA Smith and welcome to my talk on feature patterns in the Voynich Manuscript. Much research which analyses the text of the Voynich Manuscript focuses on its general properties, but I want to look at smaller patterns which exist between words and glyphs. It's something which has yielded good results before, such as co-occurrences of glyphs at the end and start of adjacent words. I want to explore what other relationships might exist, and this presentation is very much about looking at potential patterns rather than something which has been fully explored, analysed and built into a theory. Some, or maybe much, of what I'll discuss could turn out to be nothing. Also, I will need to describe the measurements I'm using to ensure that the patterns are robust, and that may take a little bit of time. And one last note, throughout this presentation, Voynich words will be presented in EVA or EVA, and I'll be pronouncing the letters individually or as groups. So what are feature patterns? Feature patterns are where a feature in one word co-occurs with a feature in another word. Features might be individual glyphs, groups of glyphs, positions in a word, or even a whole word. A feature might not even be related to a word, but rather to the structure of the text, such as a line break or image. So examples of features might include words ending in N, a word containing the glyph K, the first word in a line, or the last line of a paragraph. An example of a relationship might be words starting with D after an image. We would want to know whether this was more or less common than expected, and by expected we mean if all the features were evenly distributed. An example of feature patterns are those discussed in Smith and Ponsey, which build upon observations from Prescott Currier that words ending with certain glyphs occur more frequently immediately before words beginning with certain glyphs. So words ending with Y are more frequent before words beginning with Q, and words ending N are less frequent before words beginning with K. A comparison of actual versus expected rates for these patterns allows for a division of the glyph set into two groups. We have strong glyphs, Q, K, T, D, R, S, N, and M, and weak glyphs, O, A, Y, and the two benches, CH and SH. We also found that L was ambiguous between strong and weak. The division of the glyph set into two groups is important as it allows us to predict the relationship between glyphs at the end of one word and the start of the next. This simple table shows the predicted relationships. The combinations of strong and weak glyphs across a space show a clear pattern. Two glyphs from the same set are less likely to occur, while two glyphs from different sets are more likely to occur. These expectations will play a role later in the talk when we see some patterns which don't conform. So what features to use in this study? I'll use single glyphs and combinations of two glyphs, but due to the way the text was processed, some glyph pairs were recoded into single glyphs such as CH and QO. So some results may look like three glyphs even though they weren't when they were being processed. The feature might appear anywhere in a word, but the start and end of words was also provided as a specific feature position. The starts and ends of words are based on spaces in the transcribed text, with all ambiguous spaces treated as full spaces. Even though we could look at non-adjacent words, we'll focus on adjacent words only. The justification for this will be seen shortly. Adjacent words are those which occur either side of the same space, and line breaks don't break adjacency, nor do images, but paragraphs do break adjacency. There are known to be patterns around line breaks, but they won't be discussed in this talk. For most glyphs, they won't make a huge difference, though sifting out the patterns using line breaks as a feature is work which others, including myself, have done. In order to maximise adjacency, only running text will be used, and any labels are excluded for the same reason. The text was broken down by both language and hand. The results are based on language B text, including hand 2 herbal, hand 2 choir 13, and hand 3 choir 20. When we measure feature patterns, what we want to know is how unusual the relationship between two features is. To do this, I will use z-scores, which measures the strength of a pattern in multiples of standard deviation. These strengths can either be positive or negative, showing more or less co-occurrence between two features than expected. This standardizes a measure of how exceptional a pattern is compared to the general distribution. We'll go through a quick example to see how this works. Let's take an example pattern of a word ending Y immediately followed by a word beginning Q. The dot between them represents a space. We'll refer to the word ending Y as feature 1 and the word beginning Q as feature 2. For each occurrence of feature 1, the first thing we do is count the number of times any word occurs up to 8 places or positions before or after it. Feature 1 occurs at the 0 position in the chart, and each bar the relative position and number of words we find there. This shows the distribution of words around feature 1. Then we count the number of times that a word with feature 2, so beginning with Q, occurs in the same distribution. From the last chart and this, we can see that both features are really frequent. They have thousands of occurrences each. But in making the results we will see later, any infrequent features were simply discarded as they would not give robust data. And for each position in the distributions, we divide the number of times we see feature 2 by the number of times we see anything in that position. This provides us with the likelihood of feature 2 in each position. And I've also calculated the standard deviation for feature 2 in the 16 positions around feature 1. The z-score for each position is obtained by subtracting the average likelihood from that position's likelihood and then dividing by the standard deviation. The score of 3.7 is really high, showing the massive preference for words beginning Q immediately after words ending Y. The expectation of this pattern occurring is less than 1 in 2,000, which is among the highest scores we actually find in feature patterns. For reference, the expectation for a z-score of 3 is about 1 in 333, and a z-score of 2 is 1 in 20. So we can see how this score helps us really pick out interesting patterns. Now that we know how z-scores are calculated, we can use them to justify something I said earlier, that I would only look at adjacency patterns. This chart shows the aggregation of z-scores in the text. It shows the number of z-scores in each position, depending on the following thresholds. Orange for z-scores over 3, blue for over 2.5, and pink for over 2. The patterns are often picked up both ways, which is why the distribution of z-scores looks symmetrical. Generally, there's a lot of noise as z-scores decrease, that is blue and then pink. Due to the sheer number of potential features and feature pairs, quite a few of these are going to be false positives at lower z-scores. At a z-score of 3, practically only adjacency patterns exist. However, adjacent but 1, that is having one word between the first and second feature, do show a raised number of z-scores at 2.5 and 2. Maybe some of these patterns are genuine, but we won't investigate that here today. At last, we're going to look at some real results. We will focus only on z-scores of more than 3 or less than -3, and all will be from adjacent words, as we've said. 4 potential patterns based on the position of features, that is, whether feature 1 and 2 occur at the start and end of words, exist. The example we worked through was an end-start pattern, because feature 1 was at the end of a word and feature 2 at the start of the next, but we can see there's start-end, end-end, and also start-start patterns. We will also look at some anywhere-anywhere patterns which, as the name suggests, the features can occur anywhere in the words involved. For end-start patterns, the results provide evidence for the same division of glyphs as seen in Smith and Ponzi. The glyph L is still ambiguous, which was seen in our original work, though these new patterns provide a bit more data than before. L is always strong at the start of a word, but has a mix of preferences at the end of a word. It disprefers words beginning A and Q, while prefers words beginning K, D, and the benches CH and SH. So weak and strong glyphs are present in both. I'll say more on this at a later point. In the paper, we suggested that the end-start patterns might be caused by some kind of phonological influence. Even if not true, there is some property which clearly divides the glyph set in two. Strong glyphs have one version of this property and weak glyphs have a different version, which accounts for the co-occurrence patterns which we see. However, some end-start patterns are unexpected. We can see that dy before ka is strongly dispreferred. Patterns with lower z scores also suggest that dy disprefers any word beginning k. Even though generally words ending y occur more often before words beginning k, which is something we can see with the pattern of words ending ey before words beginning ka, showing the expected preference. Dy behaving differently might suggest that there's another property motivating this behaviour rather than the one found in other end-start patterns, a property which all words ending dy might share. Lots of researchers have seen dy as some kind of suffix, and this pattern might provide maybe another piece of evidence for that. A second unexpected pattern is the dispreference for words ending in before words beginning ai. Being a combination of strong and weak glyphs, we would expect a preference here. Most words beginning ai will end in n, but the pattern of two adjacent words ending n actually has a weaker dispreference in this one. So this pattern might apply specifically to the individual word ain after words ending n. If so, what does this mean? As with dy, some people have suggested that ain at the end of a word is a suffix of some kind, and a following ain is somehow the same thing, but just not suffixed. I don't know, and it's not a new suggestion, but it is new evidence, and it may simply point to a faulty word division on our part. Now let's look at other adjacency patterns. There are no patterns for start-end which are above our threshold of 3, and most end-end and start-start patterns might be echoes of the end-start patterns we saw before. For example, the preference of words ending in before words ending with a bench gallows plus y might be a case where the second word is complete and actually the bench gallows is the first glyph coming after the n. Likewise, those words beginning a, da, sa probably all end in L or R or N, which explains the preference for words beginning A or O immediately following them and the dispreference for words beginning QO. However, a few other adjacency patterns do seem to be independent of end-start patterns and are worth looking at. Words ending L are more common before words ending dy. Remember that we saw words ending L have a specific and unexpected mix of preferences. They don't abide by the property which divides the rest of the glyph set. The big question is whether words ending L are a class to themselves, which have their own selection patterns. Note that we also saw words ending dy have an unexpected dispreference for K. There's a potential here in these two patterns. We're seeing hints of another selectional process which works somewhat differently but interacts across multiple word endings such as L and dy. Then there are two patterns with S. Words ending S have a preference to come before words ending in and a dispreference for words ending y. Looking deeper, the pattern of words ending S before words ending in is really strong. Maybe most of these second features of the word ain. It could be linked to the dispreference for words ending n being followed by words beginning ai. Suggests some really interesting behaviour of ain specifically here. Likewise, we can see that words ending S dispreferencing words ending Y mostly involve words ending dy, though that specific pattern is actually weaker. I don't have a suggestion for what either of these two patterns might mean. Lastly, a start pattern. Words beginning SH are much more likely before words beginning QO. Now, many words beginning SH do end Y, which has a known preference for Q. The anomaly comes from words beginning CH, which, although somewhat fewer, end with Y, have a much weaker preference for coming before Q. This is kind of a subtle pattern to understand, and I think that it's CH which is out of line here, that just for some reason something is causing words beginning CH to be less common than we would expect. Let's move on to anywhere patterns, which, as the name suggests, is where glyphs can occur anywhere in adjacent words. There are lots of these, but many of them might be echoes of end-start patterns due to the rigidity of word structure which we see in Voynich words. I've selected a few which are more interesting. Words containing D are more common before words containing KE or TE. The same pattern of D before just K or T also occurs, but below our Z-score threshold of 3. Yet when we compare them with D before words containing KCH or TCH, we see a significant split. Why is there no preference at all for TCH? A Z-score of 0.3 means that it's really close to average for the distribution. The glyph combination TCH seems like a really specific target for this pattern. However, I don't have any suggestion or explanation for this. Patterns of N before words containing KE or LCH are strong dispreferences. They're also technically end anywhere patterns because N occurs at the end of a word. The dispreference of N for KE appears specific to that combination and is much weaker than for just K or TE. The same specificity is seen for LCH, which doesn't spread to other words containing L. Likewise, the variety of words which contain KE or LCH means it's hard to pin this pattern on another factor, such as the rigid word structure. Again, we have a pattern which appears strong, yet is highly specific, and likewise, like the preceding pattern, nothing really comes to mind to explain them. Lastly, there are a number of patterns where features containing E co-occur with features containing K. Now, E could just be conditioning a word ending O or Y, which is known to have a preference for words beginning K. Yet the key thing is that even though T is otherwise so similar to K, these same patterns are much weaker or entirely absent with T instead of K. None of those patterns with T are above a Z-score of 2, and some are actually mildly negative. Like all three of the anywhere patterns we've seen, the glyph K is involved and behaves differently from T. It's suggestive that the property which splits K from T, despite their visual similarity and the similar position they take in words, is really distinctive. No one expects two glyphs to be exactly the same, but it's important to note that other glyphs appear to be able to select for this property. So what have we learnt? I think the key thing is that some features seem to have their own properties. dy at the end of words, L at the end of words, the whole word AIIN might have a unique relationship with words immediately before it, and the selection of K in comparison to T. Much of this data requires more analysis, and I feel that Z-scores aren't always showing the whole picture. There is, of course, a question of whether such small relationships between individual glyphs can be found. They could all be mirages, and the real relationships are buried beneath the system which encodes the text. And with that, I'll conclude my talk. Thank you for listening, and I hope it's been interesting. I appreciate that it's been a quick whiz through a lot of data, and maybe it raises more questions than answers. I would also like to thank the organisers for their hard work in making today's event happen. We should have a few minutes for questions, and I would be happy to answer any that people might have.